I'm Professor Chuck Newman from New York University Courant Institute of Mathematical Sciences, and also now from NYU Shanghai. And our Mathematics Institute, which is in collaboration with East China Normal University, is the sponsor of this meeting. It's called the International Conference on Probability and Mathematical Statistical Physics. And so I'd like to welcome everybody and thank you for coming to the conference. The first day of the conference, as you know, are two mini courses, and I'll introduce the first one in a moment. But my co-organizer for the whole conference is Professor Shao from Chinese University of Hong Kong, and he's now going to make a few welcoming remarks also.
Okay, morning everyone, and welcome to this mini course. And Professor Newman and I think asked me whether we could organize a probability conference in May. That's last December, so that just half years ago, and we managed to have a wonderful, invite a lot of distinguished speakers, and also we think that may be better, especially for young people, to have some kind of mini course, because attended several workshops, especially in NUS, the Singapore National University of Singapore, and they have a lot of programs, workshops, and so on. So they usually they have a mini course, or they call tutorial. So I think maybe so we think it may be useful for audience to have very special talks, give two or one or two speakers, maybe give 2 or 3 hour lectures, not just one single talk. So that's why we come with the mini course today. And so hopefully that's can give us a platform to exchange and so on. And also we want to, there are many young scholars in China in probability and also maybe related areas. So I think hope that's provide a good platform for exchange ideas and so on. And hope you enjoy this mini course and also the conference. Thank you.
So the first mini course is going to be given by Professor Louis-Pierre Arguin from the Université de Montréal in Canada. And the topic is, as you can see, Extrema of Log-correlated Gaussian fields, principles and examples. And so, I welcome Professor Arguin to begin this session of the conference with his mini course.
So first of all, feel free to ask questions at any time during my talk. Okay, we're here to learn about some things, me as well. So what I want to talk about today is essentially extreme value theory. Okay, so I'm going to work with stochastic processes, and what I'm interested in for these stochastic processes is to look at the high points. Okay, so the maximum of a stochastic process, second maximum, etc. Okay, I will explain everything as we go along. Extreme value theory is well developed, except for independent random variables. We know a lot of things. For weakly correlated random variables, we know a lot of things. But we don't know many things when our variables are what I'm going to call strongly correlated. Okay, so what we want to understand, there's been recent work on this, is to understand what is the extreme value theory of strongly correlated random variables. So let's start. So first of all, I want to acknowledge some things. First of all, thank you for the invitation, the hospitality. I'm first time in China. Very happy to be here. And second thing is what I'm going to talk about, I learned from my collaborators and other people in the field. So some of my collaborators are Anton Bouvier, Nicolas Kessler, Olivier Zindi, and David Bellius on this subject. You can visit their webpage. They're really good people. And also, there are many outstanding papers on the subject recently. I won't be able to quote all of them, okay? So I'm going to put, it's not on my webpage yet, but I'm going to put like some references on all the subjects I'm going to talk about, okay? And the slides are already on my website, so you can download them even now if you want. Okay, so let's start with the mathematics. So first of all, what is what we call the extreme value theory or statistics of extremes? Okay, it's the same thing. So here's the setup. Is what we want to look at is the maxima of a collection of random variables. Okay, so the maxima of stochastic processes in general. So the setup is very simple. I have n random variables. I'm going to work in the discrete case. Okay, but what I'm going to talk about can be also applied to the continuous case. So I have n random variables, some probability space. I'm going to denote them xi. And what I'm interested in is to take a limit. Obviously, n tends to infinity, but we're looking for limit theorems. And what I'm interested in is the maximum of this collection of random variables. Okay, the law of the maximum. So this is a functional on my whole stochastic process. So what can be said about this law? Okay, so that's the essential question of extreme value theory. And then we can look at more refined questions. I'm going to mention it at the end if I have enough time. We can also look at the order statistics. So instead of just looking at the maximum, which would be, let's say, x1, I can order my collection. I can look at the second maximum x2, which is bigger than the third, etc. So I can look also at the joint law of my maxima, okay, which we call order statistics, or also extremal process. Means the same thing, essentially. And so in this mini course, actually, because lack of time, I will focus on the law of the maxima. But the principle I'm going to talk about will be applicable to the order statistics as well. And hopefully, I will have time to mention that at the end. So two things to keep in mind, okay, just to draw connection with things that you already know quite well. So where I'm looking at the maximum of this collection of random variables, so it's a functional on the whole process. And we are used to, in standard probability theory courses, to look not at the maximum, but to look at another functional which depends on everything, on all the process, which would be the sum of the collection. Okay? So always keep in mind that what we want to do here is to essentially recover results about the maximum which are similar to what we have for the sum. So for the sum, we have obviously the law of large numbers. Sorry, it's a typo here. It's the law of large numbers. And also the central limit theorems, which are limit theorems when I take this collection of random variables to be really big. Okay? So the law of large numbers we can see as, so I'm going to just write something new. The mean, mu, and almost surely in probability, depending on how precise you want to be. Okay? So we have some normalization, 1 over n. You have to normalize this collection of this functional. Do you see here? Is that good? I'll turn it just a bit. And obviously, you have, at the level of the fluctuation, the central limit theorems, which says, well, if I take my functional, now I need to subtract because I know what the order of my sum is. It's essentially mu times n. So I have to subtract this to get something which makes sense. And I also have to divide by square root of n. So I have some normalization. And I know I converge, and this is in law, to our normal 0 sigma squared. Okay? So we want to do essentially the same thing with extreme value theory, except, except that I work with the max. Okay? So here's the problem that I'm interested in. I don't know if you can read. I want to find an AN and a BN so that when I recenter my functional by AN, and also I could possibly normalize by some BN, do I converge in law to some limit? Okay, so that's essentially the same spirit as well-known standard results of probability theory. Okay? So find the right transformation, and of course, you would like to identify the limit. So for strongly correlated variables, we can achieve actually this level of precision for a couple of stochastic processes. For this course, I want to focus on principle and examples for a particular class, so we will be most concerned with at the level of the law of large numbers, so the order of magnitude, okay, which is the AN. Is that clear? Okay. So that's my goal here. So it's good to look at the history of extreme value theory because it tells you, it gives you an order of idea of the timeline it takes until a theory settles. Okay? So it's well established extreme value theory. If you just look online, there's several textbooks on it. There's several applications. But most of the applications and the theory are for, if I look at a collection of random variables which are independent, let's say IID and identically distributed, but what is important here is the very strong assumption that they are independent or weakly correlated. Okay? So what's the history here? So what we know about these questions, actually we have a complete answer for the questions that I had here, okay, or on the board about identifying the law or the limit theorem. We know that the limit laws can be only of three forms. Okay? The first type, which is the Gumbel type, tells you that the limit law, if I look at the distribution function, it can be Gumbel, which we also call double exponential, for the obvious reason. The other type is the Fréchet type, which is of the form exponential, exponential of minus x to the minus alpha. So actually I wrote down the Weibull, but that's fine. And that's only for x positive. And the other one is Fréchet, which is exponential minus x, that's for x positive, minus s alpha for x negative. Okay. The point here is that it's amazing that the limit laws can be only of three types. What I will focus on is the Gumbel class. Okay? So how long did it take to actually come from posing the problem, can I find a transformation of maximum and so that it converges in law, and what are the possible laws, limit laws, only three, to get a complete answer? It took essentially 20 years. And the first result goes back to Tippett in 1925. And what he was interested in is looking at the largest values of a sample of Gaussian. So he started with Gaussian, and that's what I'm going to do also today. That's what the title of Gaussian fields. Okay, these are easier to deal with. Okay, so he started with Gaussian, and then Fréchet, which is the first one to actually obtain, obviously, the Fréchet limit law. He studied other distribution than Gaussian and obtained the Fréchet law. And then 1928, Fisher and Tippett identified two other laws, okay? Like the Gumbel, essentially, which was also studied by Gumbel, and the Weibull law. But at that time, we didn't know if these were the only possible law, okay? And then 10 years later, von Mises actually found sufficient conditions to converge to any of those three classes. And the big theorem came in 1943, so essentially 20 years later, where Gnedenko found necessary sufficient conditions to actually converge to the three possible laws. Okay? So 20 years to actually achieve a complete answer, so that gives you hope that, okay, if you're stuck and you're not finding the answer, it takes time before the theory settles. Okay? And the first book, textbook, is 1958 by Gumbel. Very good book, by the way, Statistics of Extremes. And I put the picture of Gumbel here. So just a piece of trivia. He was a very interesting person. He's famous for extreme value theory, but he's also famous for being a very fierce anti-Nazi political writer before the war, and then fled Germany to France. He taught in France, and then went to New York, and he died in New York, was professor at Columbia for some time. So it takes time before a theory settles, so let's not get discouraged. So we know very well what ID theory is, and one of the big goals of probability theory now is to actually look at other type of stochastic processes, other classes where the variables now are strongly correlated, okay? So there's a lot of people actually working on this, and there's different fields whose quests actually are to understand what happens when you take a limit theorem, but for strongly correlated variables. I should say before that the ID theory had a lot and many applications, and one of the applications was in meteorology, looking at floods and droughts, looking at extreme events, okay? Because obviously if you have like flooding every year, you're interested, what's the distribution of the maximum flood, so I can build my, I can build a dam to protect against the flood. So there are practical applications of the ID theory. And if you look at the first page of Gumbel, he says it's an assumption that we take independent variables. But obviously he knows that in some cases this is not true. And this is what we're interested in. So what are the motivations of extreme value theory, but for strongly correlated variables? I put a couple here. There's more. So one application is in finance. There's some papers on this. It starts with Mandelbrot, and still people are still looking at these things, is that if you look at the volatility, say, of the S&P 500, and you look at the correlations between time correlations between two times, they're actually decaying quite slowly, okay? So there are actually presence of strong correlations there. And so that's, there's some applications of extreme value theory in that case. In physics, that's where I'm come from, there's several models where, so what we're interested in statistical physics in particular is looking at, for example, as the states of minimal energy. So instead of looking at the maximum, I'm looking at the minimum, but essentially the same philosophy. And those are the states that determine the physics, okay? And the energy of the states often are random. It depends on the environment. The environment, you don't necessarily know everything about the environment, so there's some randomness in it. So extreme value theory could be useful to understand, okay, the distribution of the energies, minimal energies of those systems. So for example, in spin glasses, example of systems are spin glasses, polymers, growth models, and you might have heard about KPZ, KPZ universality or KPZ scaling limit. And those are related to growth models where you have strong correlations. And these models are really also closely related to random matrices. Okay? So these people actually, if you look at random matrices, you're interested in the statistics of strongly correlated random variables. In mathematics, there's also applications, and I'm going to discuss that in the second part. If I look, there's evidence that if I look at the distribution of prime numbers, it seems to exhibit feature of strongly correlated random variables. Okay, so I'm going to explain that in part 2. It's a surprising application and still an open question, but there's some evidence that this is true. Okay? So there's several classes. Obviously, when you want to prove a limit theorems, there might be several domain of attractions. Okay? So all these different systems won't necessarily behave the same way. So what I'm going to look at are log-correlated models, as the title suggests. Okay, so it's one class of models that are strongly correlated. Okay, so just to give you like a brief outline, so that was the introduction. What I'm going to do technically, first I'm going to define what I mean by log-correlated models. I'm going to focus on Gaussian fields, a bit like the ID case, right? You start with Gaussians, they're like easier to understand. I'm going to focus on 2 examples, branching random walk and 2-dimensional Gaussian free field, that I will define, and then I will use 3 fundamental properties of these 2 examples. Those are the 3 properties of log-correlated models. Okay? So if a model you study have these properties, it's very likely that it behaves like a log-correlated model. So 3 fundamental properties, and using these properties, my goal today is to prove the first and second order of the maximum. So I'm going to work essentially at the level of the large numbers. Okay, so I want to understand the magnitude at first order, first approximation of my maximum, which is a functional of the xi. It's not the sum, it's a function. Okay, so that's going to be my goal. So there's 2 levels of refinement. Okay, this first order and second order. It's obviously easier to prove the first order. So we're going to start with the first order, and then from what we learn, try to understand the second order. Okay? And at the end, I'm going to discuss beyond this mini course what we can do. So I'm going to say a word on convergence and order statistics if time permits. And what really I want to discuss also is this relations to the Riemann zeta function and the prime numbers. Okay? So this is the outline for today. Okay. So let's start with the more technical part of the talk. If there's question, okay. So what is log-correlated Gaussian field? So here's going to be my setup. So I need an index set. Okay, my index set in the different examples is going to be Vn. Okay, and I can choose. So I want to take more and more variables in my collection of random variables. So I have a choice of parameter, and what is convenient, you'll see why, is to take 2 power n number of variables. So instead of big N, I just take 2 to the n. Okay, it's just simpler. And I also have the choice of the variance. They're going to be also mean 0, I should say. Mean 0. And the other choice I can have, by scaling, I can take the variance to be n. Okay, little n. So the parameter little n I'm going to take to infinity. It's good to take the variance to be of order n. So this is my setup. Okay, so I'm going to have x and v, which is going to be my stochastic process. I have some index set Vn, and I'm going to take, I have 2 to the n variables. I'm going to take them centered, and I have obviously a covariance. Sometimes I'm going to write CNVV prime for covariance. And what is important is the variance I take to be n. This is just a choice. Okay? So for simplicity, we assume that we have a Gaussian process or a Gaussian vector. Okay? And so there's no, so the reason we do that is, there's 3 reasons in particular, is that then all the law is determined by the covariance matrix. Okay, so it's very easy for the manipulations The covariance matrix encodes all the law. Sometimes it's easier to work with Gaussians also because you can use comparison argument, for example, like Slepian's lemma, and it can simplify some proofs. Okay? So that's also another advantage. That's a technical advantage. And also it's easier sometimes. You'll see in part 2, we're gonna need some random walk estimates, and it's easier if the increments are Gaussians. Okay? But, and I want to emphasize that the principle I'm going to talk about, I expect it to hold in general, and in some cases it's proved that it holds. Okay? So the principles here are the important things. Gaussians, it just helps you to prove what you want to prove, like doing the estimates. But if you work a little bit more, you could prove it in more general cases. Okay? So this is going to be my setup. And this index at, it's good to think of it to put a metric on it. And the correlations, so I can actually erase that. Maybe, but for now, that's fine. Thanks. Yeah, so I have like, for the second part, I'll need both, so I'll move them. So I have some space. I have some discrete space, VV prime, and we expect, okay, the correlations between VV prime, we want it to depend, so that's just an intuitive way to think about it, we want it to depend on the distance between V and V prime, okay? So in some sense, we want to relate the L2 distance, okay, I have an L2 distance, obviously, on my space, the L2 distance between my xn, and I can think of it, and I will think of it as a distance in Vn, okay? Yes? Oh, sorry, it's all little n. Yeah, that's the unfortunate change of, thank you. It's the jet lag. It's the jet lag. Yeah, it's a bad idea to change notation in the middle of your slides. Thank you. Yeah, let me know if there's some. Good. I see Federico here. Okay, so now I want my Gaussian. What do I mean by log correlated? Well, it's clear from my definition that, I mean, from the setup, I have a certain distance. I want the correlations to decay slowly with the distance, and what we're going to take is to decay logarithmically with the distance. Okay? So the correlations between V and V prime will be, okay, approximately the log of 2n over the distance between V and V prime. Okay? So that's a very slow decay of my correlations, okay, much slower than any power law or exponential, obviously. So many points are quite correlated. Okay, so if my distance between V and V prime, so you can think of, okay, the diameter of Vn, it's good to be of the order of my number of variables. Okay, so what you see from that is that they're essentially independent if the distance is the order of the system. Okay, so the log of 1 is 0, so essentially independent. If my distance is small, let's say distance between V and V prime is 1, of order 1, what I pick up is log of 2n, it's essentially n. It's the order of the variance. Okay, so I have quite strong correlations between the point, and even stronger than that is I have many points that are strongly correlated. Okay, So I'm seeing here there's an exponential number of points whose correlation with V, okay, so if I take V, okay, I take V and I look at all the points, whoops, V, and I look at a certain neighborhood of V, and I look at the neighborhood, I look at the number of points whose correlation with V is the order of the variance. Okay, so a constant times n. So that's what I wrote here. So take R between 0 and 1 and look at the neighborhood, the V primes, whose correlations with V is bigger than R times n. So a fraction of the variance. Okay? Then from this, it's easy to see that it should be something like 2 to the n, the order of my system, over 2 to the Rn, okay? Which means that this neighborhood is exponential in n. Okay, so I have many, many points that are strongly correlated. And by strongly correlated, I mean the order of the variance, okay? R times n. Okay? So log-correlated is very simple, is that the correlation decays logarithmically with the distance. Is that okay? So that's just the definition. Let's look at the first example, branching random walk with Gaussian increments. So it's a branching random walk on a binary tree, which is the simplest maybe example of branching random walk. So what's my Vn here? What's my space? The space is going to be the leaves, not the whole tree, okay? It's going to be the leaves of a binary tree with n generation. Okay, so here I have, so that's just the root. I have 3 generation. So I have 8 points. And so my index set is the leaves of that tree. I have 2 to the n number of variables. Now, so to each point of my space, I associate a Gaussian variable. And in this case, it's very easy to define the variable. What we're going to do is put on each edge of this tree an increment, YL, which is the normal 0, 1. Okay? And the IID on all my trees. So all my edges, okay, I associate a random variable, Y. Now, the value of x and v is simply all the increments on the path going from the root to v. Okay, so if I take v here, what is x and v? So I have this path. So I add y1v, y2v, y3v. Okay, very simple definition. It's a very simple definition, but you have, defining this, define a Gaussian field with really strong correlations. Okay? So why is that? So if you look at the variance, well, the variance obviously is just adding the variance of all my increments. So it's the number of generations, so it's n. Okay, so I'm in the setup, I mentioned variance n, 2 to the n variables. If I look at the covariance now between x and v prime, so I have v and v prime. If I look at the covariance, well, what happens is that at some point, v and v prime, the path just split up. And my notation for split up will be v wedge v prime, okay? So that's the most recent common ancestor in v and v prime, which is where the path split up. So obviously, after they split up, the increments are independent, okay? So the variance between x and v prime is simply the common part of the path. I have to sum up all my increments. Okay, that's my notation here. And so in the end, what I pick up is simply the generation. Okay, the number of increments I add up is simply the number of generations where they're the same. So it's essentially the generation where they split up. So essentially, it's exactly the generation where they split up. Okay, so that notation I'm going to use often. Okay, so get used to it. So v wedge v prime. Okay, so it's just the ancestor of V and V prime. Now, I told you that I have strong correlations. I have many points that are correlated, strongly correlated, so it's easy to see here why. So if I look at this neighborhood of V, okay, which has a strong correlation, so something like R times N, or even stronger than that, how many points do I have? Well, those are the points that have split up with V, okay, after generation Rn. Okay? So if this is Rn, okay, that level, that's V, it's all the point. Obviously, if the correlation is this or stronger, they have to split up right after. Okay? So along this generation, so this is all the points here whose common ancestor is the same as V at the level Rn. So how many points are there? Well, at the level Rn, I have 2 to the Rn points. Okay? It's a binary tree. So at generation Rn, I have 2 to the Rn points. Okay? So the number of points we share the same ancestor as V at this generation is simply 2 to the n over 2 to the Rn. Okay? So I have many points that have a strong correlations with a given one, okay, order of the variance. It's exponential in n. Is this clear? Okay? So I will have pictures like that often. It's good to draw it. Now, let's look at another example, the two-dimensional Gaussian free field. Okay? So here, I'm going to need my notes. So the two-dimensional Gaussian free field is another log-correlated model. So what is now my Vn? Now my Vn is a square box in Z2 with 2 to the n points. Okay? So this is just the choice of my parameterization, 2 to the n points. That's my Vn. I'm going to take n large. Okay, so to each point V, associate a random variable x and V. Okay, so you see the grid here. Okay, so that's my Vn. Now, what's my correlations? Okay, so my Gaussian field is determined by my covariance matrix. So I just have to define it. And what we take is to take the correlations to be the following quantity. Okay, so I start a simple random walk Sk at my point V, okay, right here. And then I count the number of times that I hit, that's an indicator function, that my random walk Sk hits V prime before exiting my box Vn, okay? So I count the number of times that I hit V prime starting at V for a simple random walk, and I average over that, okay? So it's very simple definition. So I have V prime, I start a random walk, let's say I hit V prime here, okay? I come back here, oops, I haven't hit V prime. Hit V prime, come back here, boom, boom. At some point I exit my box, so here for this random walk, I hit V prime twice. Okay, so my correlation here is the expectation over V of this random walk okay? So obviously I can actually add a constant Here I don't lose anything. Okay, it's just that I want to normalize my variance to n. Okay, so it's convenient to actually put a constant. So now, two things that, okay, so I defined this quantity, but two things that are good exercises, and that might be surprising at first sight, is that this quadratic form, CVV prime, well, it's symmetric, which is not even clear to start with. Okay, I started walk at V prime. So it's not even clear that my covariance matrix is symmetric. It's not hard to prove, but it's not direct. And the other thing is that it's positive definite. Obviously, if I have a covariance matrix, I need this covariance matrix to be positive definite. And so it's a non-trivial, it's an exercise to just show that this quantity is also positive definite. The nice thing, with that kind of definition, here I use the simple random walk, okay, to define my covariance matrix. It's just an auxiliary process to define my covariance matrix. It has nothing to do with the actual realization of my Gaussian field. It's just a way to define a covariance matrix. But instead of simple random walk, I could have used something different. I could have used another Markov process. And if this Markov process is reversible, I'm going to have these two properties. Okay? So a simple random walk is what we use, okay, to show these two things is the fact that it's a Markov process and it's symmetric. Good. Okay? So this is my covariance matrix. Okay? And this covariance matrix, if you do some exercises, you realize that it satisfies the following thing. So the way to prove these things is to use the Markov property of the simple random walk. Okay? And if using the Markov property, okay, conditioning on the first step, okay, if you condition on the first step that my random walk takes, I can prove the identity that, so I'm in 2 dimensions, that that's Cn, if V is not equal to V prime, and if V is equal to V prime, it's 1 plus 1/4 sum over okay. So by this I mean the neighbors of V. Okay, so I have 4 neighbors, north, south, east, and west. Okay, so I have this identity, which is easily proved using the Markov property of the random walk. So it's if V is equal to V prime, and if V is not equal to V prime. Now, if you play with this a bit, I recall what is the definition of the Laplacian with discrete Laplacian. So if I take a function f okay, if I take my function f, this is simply, so I take the derivative in every direction. So I look at all the neighbors. And what you get is the following. Okay? So the discrete Laplacian in any dimension is simply Laplacian of V is the sum of all the neighbors of the difference. Okay? It's the exact equivalent, or analog, I should say, of the Laplacian and continuous. Now, I could add 1/4 here, okay? And if I add 1/4, okay, I see that I get the average of F around V, okay? So it's very similar to what I have here. It's exactly the same, okay? So what I have here, if I subtract FV, which I have here, I recover the Laplacian. So I'm going to use now the, well, I guess I can erase this one. So all this to say that my covariance matrix satisfied the following equation. Minus 1/4 the discrete Laplacian is equal to the Kronecker delta at V of V prime. Okay? And this is the equation for Green's function. Green's function of discrete Laplacian. Okay? So you'll see in Gaussian free field papers that this quantity is simply the discrete Laplacian, the Green's function of the discrete Laplacian. That's how you show it. Essentially, it's from this identity, but this identity is very simple. It's simply by conditioning of my first step. Okay? It's to use the Markov property of the underlying random walks. Okay. So that's a little. So now I'm going to bring the other board. So I'm taking my time talking about the Gaussian free field because I think Federico is going to talk also about it. So now I have the covariance matrix. What is the density of my two-dimensional Gaussian free field? Okay, so I have a Gaussian process, X and V. Can you see? So what's the probability it belongs to some set? Well, it's the integral over the set of some. Okay, so for all the V, so I just for all the V, I'm just going to put a dot. So my density, it's the Gaussian density, so it's exponential. I'm going to have minus a constant. What is important is here, so what's the quadratic factor? So the quadratic factor is the sum over all the pairs that are neighbors, okay? So on all the edges, product over V belongs to Vn dxv, okay? I have to divide by some normalization constant, okay? So another good exercise is to take this Green's function of the discrete Laplacian and invert it, okay? Because what I'm going to have here, okay, it's a Gaussian field, so what I have in the exponential is it's going to be the inverse of the covariance matrix. So a good exercise is to invert the Green's function of the discrete Laplacian and see that this is what you're going to get, okay? And now we see that actually the Gaussian free field from the density is not that complicated. What we do is, if you look at the increments, and by increments I mean the difference, okay, the gradient between 2 points, neighboring points, well, this is actually a normal 0, 1, not necessarily 0, 1, but it's a normal variable, and the increments are independent, okay? So the height difference between points, actually they're independent. So it looks a bit like a simple random walk, but more than one dimension, Okay? So if you look at my image I have here, so I put one realization of Gaussian free field. I think it's 40 by 40 grid. And to each point, so if you look at the color, that's the height. The red points are the highest. Okay? And we see that obviously we have strong correlations between the height of my points. Okay? Because, well, we'll see from the increments. Okay? That this, if one point is high, the other point around them, we see from these clusters, are also high. Okay? It's not like white noise. If I put ID variables everywhere, then what I'm going to get is something which is really, really, not, how can I say, like rough. Here it's rough, but at least there's some correlation that smooths out a bit. And so if one point is high, the other point is high. So it's some regularity, though it's still kind of rough. Okay? Good. Okay, so that's Gaussian free field. Now, I could look at my covariance and try to see what it means in terms of the distance between V and V prime. Okay, I told you there's always a metric underlying my correlations. Here, the metric, well, that's just the Euclidean metric on my box. Okay, it's just the distance in two dimension. So how does my correlations behave with the distance? I want it to decay slowly with the distance. I want it to be log-correlated. So that's another exercise to show the following. If I look at the variance of my field, it goes like the log of the number of points with a constant goes like n. I choose my constant here in front, so I get what I want. Okay, so I can always do that. I can normalize. And if I look at the covariance between two different points, okay, that's again an exercise. They should decay logarithmically with the distance. Okay, this is what I had for log-correlated. So I have the log of my number of variable divided by the distance, okay, square, the distance between V and V prime, okay, in the box. There's a constant here. Those estimates are Green's function estimates, okay? So they're not, there's going to be some constant, something of order 1 when you do these estimates. But they don't matter much because we're taking n tends to infinity, okay? So we don't have to worry too much about these. They won't change the statistics of extremes that much, okay? So here I put just this little disclaimer. These two Green's function estimates are true if you're not too close to the boundary, okay? What happens if you're close to the boundary, the correlations are in terms of a simple random walk. But I stop my random walk once I exit. So if I'm close to the boundary, I can exit right away, okay? So that essentially decouples V and V, 2 points, V and V prime, okay? It also makes a variance which is, I don't return as often to my point because there's a big chance I exit right away. So when you actually want to prove things, rigorously for the Gaussian free field, there's some estimates that have to deal with this, okay? But that's not part of the principles, say, of how to deal with this field. That's just a technical aspect that you just have to do at the end. But this won't influence much. Good. Good. Okay, so this is my 2 examples. Other questions on the Gaussian free field before I move on how to prove things? Okay? Good? So don't feel free to interrupt me. There's no problem. Okay, so now those 2 models are quite different. Okay? If I look at the correlations, they're kind of similar, but we agree that all in all, they seem very different. The space Vn is quite different. Tree for one, for branching random walk. For 2-dimensional Gaussian free field is just a box. So what are the common aspects of these 2 processes we can work with to prove the same results? Okay? So there's 3 properties, so that's an important slide. So there are 3 fundamental properties of log-correlated random variables, and these are the properties I'm going to use to prove things. Okay? So those, in fact, like enter in the principal part of my talk. So what are they? There's the multi-scale decomposition, okay? Multi-scale decomposition, that's the first one. The second one I call the self-similarity of scales, and the third one I call the splitting of the scales. So let's use the branching random walk to illustrate these, because they're quite obvious for the branching random walk. Okay, so the multi-scale decomposition is the decomposition into increments which have the same law and are independent. But remember my definition for the branching random walk, what is the field at V? It was simply adding the different increments, and they were independent, and they had the same law. They were normal 0, 1. So in that case, that's quite obvious. I can decompose my field this way. So the scale here, what are the scales? They're the levels, the generation. Okay, I have n scales. So that seems obvious now, but when we get to Gaussian free field, it's going to be a bit different, but keep the tree in mind. Okay, so I have n scales, and those are my increments. And I can even define, if I take a v at the end, I can define what I call the field at scale k of v. That means I simply add up my increments from 1 to k. Okay? So the field at this scale, at this level, for that point is simply adding these two. Okay? Very simple, but again, when we're in a different setting, okay, that's going to be like not as obvious. So it's good to just hammer it. Okay, so that's multi-scale decomposition. That's the easiest. Now, what about what I call the self-similarity of the scales? For a given V, I can look at the neighborhood of points, the V prime, which branched. Okay, so this is the common ancestor. I told you my notation, which branch after generation or scale L. Okay, so this is my let's say this is my L. So what is this neighborhood? It's like all these points, okay, that share the same common ancestor at scale L. How many points do I have? 2 to the n over 2 to the L, okay, in that neighborhood here of points, okay, that branch from V after scale L. Now, if I take x and v prime, so the value of the field, and I subtract the value of the field at scale L, so that means I subtract the common part of my points. What I end up with is really simple. It's just that little subtree here, okay? But this is also a branching random walk. This is a branching random walk that started at that point that has n minus L generation. Okay? So that's what I mean by self-similarity of scales. If I subtract the common part, I end up with a branching random walk on my smaller space. It's not Vn now, it's just the neighborhood of V. Okay? Has the same law. That's the second property. And the third one is the splitting of the scale. What do I mean by that? If I look at 2 points, again, V and V prime, and I look at their increments at each scale, okay? Well, V and V prime, if the increments, okay, they're higher than the point where they split up, they're the same, okay? So the increments have variance 1, okay? If V and V prime split up after scale L. And they're independent if I look at a scale L, which comes after the point where I branched out. Okay, for example, if I take these two scales, so that's after they branched out, they're independent. Okay, so those are the 3 properties I'm going to need. Okay, so I'm going to write this up, so we don't need this anymore. I can erase it. So that's maybe the most important slide. So the first one, I'm going to keep that. So the first one is the multi-scale decomposition, which just means that I can write x and v as the sum of all my scale from 1 to n, and the increments are independent, identically distributed. The second one is the self-similarity. The self-similarity of scale. And the third one, it is splitting. Okay? So I'm going to just draw a picture. So I have v and v prime. That's the point, the scale where they split up. Okay? So if I take an L, which is smaller than v prime, my increments are the same. And if I take an L, which is bigger than v and v prime, my increments are independent. Okay? Obvious properties for the branching random walk, not so obvious for the Gaussian free field. Is that okay? Good. Now, let's show why these three properties also hold for the Gaussian free field. Okay? First of all, just a reminder, we're working with Gaussian variables. Okay? So a good way, maybe the best way to think about those variables is to think of them as vectors in an L2 space. Okay? That simplifies a lot the intuition. So it's good to see this collection of variables in a Gaussian Hilbert space. So what does that mean? Well, I can think, so it's just the L2 space, okay, of my priority space, and those variables are just the vectors. So if I take the variance is simply the norm square of the vector, and if I take the covariance is simply the inner product. If I look at the conditional expectation in that setup, that's simply an L2 projection. Okay? So if I take the conditional expectation of my fields and I condition on other variables, it means I project on the subspace spanned by those variables, by those vectors. Okay? So I can write it, if I project, that means I can write it as a linear combination of those variables. Okay? So just orthogonal projection in L2 space. Okay? And I can also decompose any variable in two independent increments by just, it's exactly like an orthogonal decomposition. So if I have a collection of, or a subspace spanned by a collection of variables, I can write any variables x and v as the projection on that subspace, okay, plus the orthogonal part of the, okay, of my variables, so orthogonal to the subspace. Okay, that's elementary, but it's really good to keep in mind when dealing with Gaussian fields. That's one of the aspects that help you when you work with Gaussians. Okay? So why are these three properties true for Gaussian free field? Okay? So the multi-scale decomposition is the easiest one. And you can always do it. This has not anything, has nothing to do with log-correlated. Okay, so you could always do it. And it's a very simple thing. So I want to write my process as a sum of increments. Okay? So what I'm going to do, I have to define what I mean by this ancestor. I haven't defined it yet, right? For Gaussian free field. For branching random walk is where you branched, okay? But I know that for branching random walk, the number of points that just branched with a given point v, let's say at scale L, I have 2 to the n minus L points. So what I'm going to do is I'm going to define this VV prime to be the largest L such that my distance square, which is essentially the area, okay? The area of points, the area of a neighborhood of V, I want it to have 2 to the n minus L points. Okay, so I do the exact, analog. The exact analog as branching random walk. I take a V, I center, okay, V is the center of this ball, like in my picture here. I look at all the V primes, okay, for which the distance square is small n 2 to the n minus L approximately, so that I have 2 to the n minus L points, okay, in this neighborhood. I do the exact analog as branching random walk. So note that, so in branching random walk, the L were the scales and the axis was going down, okay? L, that was L equals to 1, larger L equals to n was the last level. Now, as L increases here, my neighborhood becomes smaller and smaller, okay? So the direction of L goes in this direction. Okay, it's a bit confusing because it's minus L, but it's very easy to verify. So the neighborhood decreases, okay, as the scale increase. Now, for branching random walk, I had the field at scale L. The field, whoops, sorry. The field, okay, so the field at scale L, we're just adding up the increments of my points up to level L, generation L. Now, what I'm going to do here is I'm going to define XLV to be the conditional expectation, so the projection of my points on what? On all the points outside, okay, my neighborhood with 2 to the n minus L points, okay? So this means a neighborhood with 2 to the n minus L points. I'm looking at L's that are bigger than that, okay? So I'm going to actually condition, so the conditioning is everything that is outside that neighborhood. Okay? So here the color is inside. It's a bit confusing for other reasons later. Okay? But what I'm conditioning, I project my field on points that are far away. Okay? And if you think about that, that's exactly what I was doing with the branching random walk. Okay? Because if I want the common part was the part that if I project with the points outside my neighborhood here, I will still get. Okay? So I project some point outside the ball. Okay? That's the only thing we have to know at this point. Now, whoops. Okay. Now, once I have this field at scale L, I can define the increments just by doing this difference, okay, between two different fields at scale L. Now, what I've done is I can do all the time. I can project on any kind of variables. I just decided to project on variables that are outside. Now, notice that the scale, so my increments, okay, are actually independent. Okay? Why is that? Because what I'm doing here is essentially, it's exactly a martingale difference. Okay? This is a martingale difference. Why? Because this is a martingale. Okay? Because what I'm doing is I take a variable and I project on other variables, but if you think about it, I told you the L, the direction goes like this, so I have a filtration, okay? So I project, so I have more and more variables. As L increases, I project on more and more variables because I project on what's outside the ball, okay? So what I have here is a martingale because I have a filtration, okay? So I'm taking neighborhoods that are smaller and smaller. What I project on is bigger, more and more variables. So this is just a martingale difference, okay? So the increments of a martingale difference, because I work with the Gaussian fields, they're independent, okay? They're orthogonal, therefore they're independent. Another advantage of working with Gaussians. So again, this is always possible for Gaussian fields. Okay, so that's the first property. I can always do that. Now, what's special with the log-correlated models, and in particular Gaussian free field, is the second property, the self-similarity. Okay? So now what does this mean, this self-similarity? Well, I have to do the same thing as I did for branching random walk. So I take a given V, and I look at all the V primes, okay? And I'm looking at the value of the field. Okay, I want the subtree. So I'm taking the value of the field minus the field at scale L, okay, minus the upper part. Okay, and I want to show that if I restrict to all the points that branched after, okay, that branch after L, that means all the points are close, okay? So I'm hiding my, okay, so that means all the points that are close. Then I want to see the original law. So this is a lemma that I won't prove, but this is not too hard to prove with what I told you about the covariance of the Gaussian free field, okay? You're going to have to use the Markov property of the simple random walk that defines the covariance matrix. But that's a good exercise. So if I now do it, this is true for any neighborhood A. Okay, in my case, I take a neighborhood that has 2 to the n minus L points. But it's true for any subset, any box A. I project on what's outside A. I call that XAV just for notation. So if I take my field X and V minus what I project, minus the projection of what's outside my set, it's also a Gaussian free field on A. Okay? So it's also a Gaussian field whose covariance matrix is given by a simple random walk, but now my box is not a whole Vn, it's A. Okay? So it's a Gaussian free field on A. That's a good exercise to prove that. So in our case, A complement are just as I said, are just the points outside my box. Okay? So what does that give us, this self-similarity? Well, that's good to know in itself, but it also gives us other things. So if I take this increment, xnv minus xlv, okay, what comes after in the subtree? Well, I know this is the variance. The variance of this should be the variance of a Gaussian free field on A, but I have 2 to the n minus L point, okay? So that means, okay, that I have n minus L for the variance, okay? Think of it, I had 2 to the n points before variance n, I have n minus L points now, I have a variance n minus L, okay? And because of orthogonal decomposition, here I have an increment orthogonal to the points outside. Okay, so the orthogonal decomposition of x and v is this increment plus this increment. okay, XLV. So the variance of this should be L, okay, because the variance of the whole thing is N. That's just the square norm is my variance. So I have variance L. Okay, so that means that if I put increments, my increments YL, that for every L, my increments are just Gaussians of variance approximately 1. Okay, 1 plus little o of 1. Okay, so this self-similarity gives us. Okay, my goal is to show you that the tree for branching random walk is the exact same thing as Gaussian free field. Okay, now we have two properties. And now the third property is the following, is the splitting, okay? The splitting was that, okay, if I look at points, it's the picture I have here. If I take V and V prime, if I look at points that branch at V, wedge V prime, at lower scale, I should have an increments which are exactly the same, or approximately the same, and below, for scales that are finer scales, they should be independent. Okay, so that's the splitting. Now, to prove that, you need an interesting property of the Gaussian free field, which is the Markov property. Okay, what does it say? Again, if I take any sub-box of my Vn and I project my vector, my variable, on what's outside that A. Okay, so it should be, a priori for any Gaussian field, it should be just a linear combination, it's a projection. So it should be this vector should be a linear combination of the variables in a complement. What the Markov property tells you for the Gaussian free field is actually this is simply a sum over the variables which are on the boundary of A. Okay? It's simply a linear combination, okay, of the variables outside A. So when let's say I take this big circle and I condition of what's outside for this variable, actually what I get is this, okay? So the projection only depends on the boundary here. Same thing here and same thing for like the finer scales. Okay, so the Markov property tells us that if you project, that's what you get. Okay? So that's good, and if you think about it for a second, that gives you what you want. So what we want, we want to prove two things. So let's start with the first thing is that, let's start with the independent part, okay? So I want to prove that if I branch in scales that are lower, okay, if I look at increments in the finer scales, they should be independent. Okay? But this increment, so let's say this circle is the scale L, okay? So this increment xnv minus xlv, okay, it should be independent of the increment. So this, if you want xnv minus xlv, are all these increments here. I want to show that they're independent from all these scales of V prime that are lower. But the scale of V prime that are lower, this increments depends on the smaller circles. Okay? Depends only on the smaller circles. And this guy, it's an orthogonal increment of what's outside, okay, this scale L. So the smaller increments are obviously outside of that circle. Okay? So they're independent. So independence of the scales at the lower level comes from the Markov property. Okay? So that's a nice exercise also to prove. And everything is derived from the formula for the Green's function. Now, I handle the blue circles. What about the higher scales? If I split at a certain level, what about the scales above? Well, they should be essentially the same. Okay? This should be in branching random walk. It was the common part. They were exactly the same. So here they should be approximately the same. So why is this true? This is, again, a lemma. It's a bit harder to prove, but it's not. It's just, again, an exercise on random walks. So if I look at XLV minus XLV prime, so it's the field at scale L for V, the field at scale L at V prime, and I'm looking at a scale L which is above. Okay? So what this lemma tells you is that the norm of the difference, okay, is of order 1. Which tells me the following, which tells me that actually, if I look at the covariance, okay, between XLV and XLV prime, it should be of the order of the variance of XLV squared, which is equal, okay, to L. And L, you do that from every L. I have L increments. So that means that every increment should be essentially of order 1. Okay? So what I'm doing here is actually very simple. It's simply, like very simple Hilbert space geometry. Okay, I have two vectors, XLV and XLV prime. Okay, the norm of these vectors is L. Okay, think of L as large. And what this lemma tells you is that if I look at the difference is this vector here. Well, this norm of this vector is of order 1. Okay? And these guys, the square norm is of order L. Okay? Whoops. Ooh. Hopefully it's not broken. Well, I'll do that at the break. So, oops, where's the? Okay. So, obviously, you see here that the projection, if I take the inner product between XLV prime and XLV, it should be essentially, so that if I take the orthogonal projection, well, the size, the norm of that orthogonal projection should be of the order of L. Okay, I'll think of it as much bigger than order 1. Okay? Then this is what this is saying. Okay, so this isn't saying much. Okay? So when you prove that the covariance is essentially L, okay, which is the variance of one of the vector, so the increments should be essentially the same. Okay? So what I have up there is not 1, but it's really 1 plus little low of 1. Okay? It's not exactly 1 like branching random walk, but it's simply just little o of 1. Okay, now I need to repair because I need to move on. Oh, unless I use this. I'm going to use this. I need to point, though. So it's time to think about a question to ask me. That's good to have music during the. So I'll just. So I define you the 3 properties that are important for log-correlated models. Okay, we have done most of the work. Okay. Now I told you my goal today was to show you that for 2-dimensional Gaussian field and Gaussian branching random walk, and for other models that have these properties, I can prove things about the maximum. Okay? So what we can prove is what I call the first order of the maximum. You have it here, which I take the maximum and I divide by n. If I take the maximum and divide by n, what I get is a constant. Okay? Almost surely in the limit. That's at the level of the law of large numbers. Now, it's slightly different than for the sum here because we can go to a finer level. For the central limit theorem, I just have to subtract the mean times n to get a non-trivial limit. And I have also to normalize. It turns out that for the maximum for Gaussians, you have to not only subtract this constant time n, but you also have something of a lower order of order log n, or a higher order, I should say. Okay? So that's what I call the second order of the maximum. So if I subtract a constant times n divided by log n, what I get is minus 3/2. I put in red because it's going to be important. 1 over the constant I got before. Okay? So this is at the level of the law of large numbers. And the convergence here is in probability. Okay? And what this shows is the following, is that the maximum of log-correlated Gaussian fields is a constant times n minus a constant times log n plus little o of log n. If you could go beyond, and for certain models show that this order of little o of log n is actually order 1. Okay? Then you subtract by this and you try to prove a fluctuation theorem. And we're going to compare with IID. So if I compare with IID, what's the result for IID? For IID, you're going to get the same constant at first order, and that's important. Okay? But you get a different constant at the second order, in the order log n. Okay? We're going to do the exercise for IID variables. Okay? So what is surprising at first, even though we're looking at strongly correlated Gaussian fields, the first order is the same. Okay? So if I look at how big my maximum, what's the order of the magnitude of my maximum, it's the same at first order. I have to go in order log n to see a difference. Okay? There'll be a difference in the fluctuation as well. Okay? So that's the important thing here, and that's going to be that's one of the take-home message. Okay? Good. I think we have time to talk about, just before the break, talk about the IID variables because that's easy. Okay? So that's the standard thing. I want to find AN and BN so that the maximum of my collection of random variable converges in law. Okay? So we can already go at the level of fluctuation for IID. It's much easier. Okay? So obviously for IID variables, if I look at this quantity, I can simply write it. If the maximum is smaller than x, then all my variables are smaller than x. I have 2 to the n variables, so this is the same thing, and they're independent, so I have a nice factorization. This is the probability that 2 to the n variables, okay, are smaller than my level I'm looking at. And I can write it as 1 minus the probability that I exceed xbn plus an. Okay? Now, this is easy now to solve that. So I want to get something substantial in the limit. To get something substantial, I need this probability to decay like 1 over 2 to the n. Okay? Because 1 minus 1 over n exponential n, the limit n tends to infinity, is an exponential. So I am in the form of, asymptotic form to get an exponential. I just need to ensure that this probability goes like 1 over 2 to the n. Okay? So I deal with Gaussian. So everybody should know the Gaussian estimate. Okay, so I'm looking at large value of Gaussians. If I were not dealing with Gaussians, I would have to look at the same thing, the right tail of my distribution. In our case, for Gaussian, it's slightly easier. So I wrote it for variables for variance n. So what's the probability that a Gaussian is of variance n is bigger than a? Is essentially like e to the minus a squared over 2n. So the value of the density at the point a, okay, notice my variance is n, okay, divided by a over square root of n. Okay? The square root of n comes from the variance. If you had variance 1, then I would have this and no square root of n. Okay? And then something plus constant plus little o of 1. Okay? So if you deal with something else with Gaussian, you would still have to deal with that. You would have to know the right tail of your distribution. Okay, now I told you that, okay, so I want this, okay, times 2 to the n to go to a certain limit. Oh, I can use this. It's good. To get a good limit, I need. Oh, okay. Thanks. Sorry. Okay, I need this quantity, which are my large value of my Gaussians, times 2 to the n to converge to something. Okay? So I put in red what's going to cancel what. Okay, so to get something in the limit, I need an squared to cancel this 2 to the n. And what's the form? It should be square root of 2 log 2 times n plus little o of n if you do the calculation. So the first term that you have to deal with is the, to kill the term which has the most effect, which is 2 to the n, obviously. So I want this an to satisfy that. Yeah. So here I work at x equals to 0, okay, because it should be true for all x. So forget about the bn. X times bn is just 0. Now I need to also cancel, this thing has to make sense in the limit. So what is this little o of n? If you do get a calculation, okay, so an divided by square root of n, I already know what's my first order here. So it's c times square root of n. So if I put it back in the exponential here, I have e to the minus an squared. It has to cancel this term, okay? And if you look at it, if you do the calculations, the little o of n needs to be 1 over 2 to the c, and the log n is missing. Okay? Sorry, it's a little typo. And if you do the calculation again, bn equals to 1 works. Okay, so actually with the parameterization I took, it's one of the reasons I took this parameterization, you don't have to this normalization bn is equal to 1. Okay? So what you get after this calculation is this simple proposition that if I have 2 to the n IID Gaussians of variance n, okay, so now I have no correlations, my recentering term is Cn minus 1 over 2 log n, and if I normalize by this, recenter by this, my normalization is 1. What I end up with is the exponential, which comes from this 1 minus exponent 2 to the n. And then the x, if you add the x in your asymptotics, you exactly get the Gumbel distribution, okay, that I started with. Okay? And this c is equal to square root of 2 log 2, which is going to be the same c we get for log-correlated models. Okay? So it doesn't seem to work, but that's okay. Okay, so just to sum up, for ID variables, what I get for first order is a constant times n. Okay? So this you get from that proposition. This proposition is stronger. It's actually up to the fluctuation. But if I divide by n, here, everywhere, I would get the first order. Okay, so I get square root of 2 log 2, and you can, it shows convergence in probability, but the convergence is good enough to actually upgrade it to almost sure convergence. Now for the second order, again, you get it from the stronger theorem. If you divide by log n, you realize that the constant in front of the log n is minus 1/2, okay, divided by c. And what was important here, and that's going to come back in the second part, the quantity that was important for convergence was the following quantity. It was the mean number of exceedance. Okay? So what's an exceedance? The number of exceedance is the number of variables, okay, whose value exceeds a. Okay? And the mean number of exceedance, okay, so I just ask if the first variable exceeds a, the second, the third exceeds a, etc. So it's linear. Okay, so the mean number of exceedance is my number of variable times the probability that I exceed. Okay, that's exactly the quantity I was dealing with to get a non-trivial limit. It was the mean number of exceedance. Okay, and the probability that the maximum is bigger than a is exactly the same question of asking that there's one variable that exceeds a. Okay, so I want this number of exceedance to be bigger or equal to 1. Okay, so how are we going to look at the maximum the next part? It's going to be by looking at this exceedance. Okay, I want the number exceedance to be bigger than 1 if I want my maximum to be bigger than a. Okay, so I think it will be a good time to stop, and then we're going to start in the with second part after the break.